Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, in today's lecture we are going to talk about the Slaters rule. Basically, Slaters rule are used to calculate the value of the sigma, that is screening constant, and the value of the Z effective atomic number. So first of all, in the Slaters rule, we have to write down the electronic configuration of the atom for which we are doing the calculation of the Z effective. So first write down the electronic configuration and then group them according to the value of their n. As you people know that we write the electronic configuration according to the n plus L value, but for Slater's rule we don't have to use it in that way. We have to group the you can say different subshells according to the value of their n, that is the principal quantum number. So first of all we have a supposed atom, that is A. Its electronic configuration is written in this manner: 1s, 2s, 2p, 3s, 3p, 4s, 3d. And you people know that this 4s and 3d is written according to the n plus L value. So we have to group it according to the n value. So 1s, 2s, 2p, they are kept together. 3s, 3p, 3d, they are kept together, because according to the n value the 3d must be with the 3s and 3p, and then we move toward the 4s. The next step is select the electron for which you are going to calculate the value of the sigma and the Z effective. And important point is that contribution of electron outside the mentioned or selected group is taken as 0. For example, if you are calculating the sigma value for any electron present in 3p and still the electrons are present in the 4s, the contribution of electrons present in the 4s would be taken as 0, because that electrons are present outside the selected group. That's very important. As far as Slater's rules are concerned, there are two types of the rules that are used for the calculation of the ns and np electrons and n-1d electrons. So you have to focus upon the rules because there are slight differences between the two types of the rules. First of all, we would look at the rules that are used for the calculation of the effective and sigma value for the ns and np electrons. So first rule says that we have to take contribution of various electrons present in various subshells and shells for the calculation of sigma value. So 0.35 contribution for each electron remaining in the nth shell. If we are calculating the Z effective value or the sigma value for any electron present in the 3p. So 0.35 contribution or value is taken for each remaining electron in the nth shell. What does nth shell mean? It means it is that shell for which or any subshell of the which we are calculating the value of sigma. If we are calculating the value of sigma for 3p, the remaining electron in the 3p and 3s would be taken in this category, that is 0.35. The next rule says that 0.85 for each electron in the n-1 shell. So if we are calculating the sigma value for any of electron present in 3p, 2s and 2p would be taken as the n-1 shell. So 0.85 for each electron present in the n-1 shell. And the third rule says that one value for all the electrons present in the inner shell. Here the only inner shell is 1s, so one contribution is taken for each electron present in the inner shell. There may be greater number of inner shells, but you have to take all the electrons, sum all the electrons and then multiply them with 1, because the contribution of all the inner shell electron is taken as 1. Here's an example that would show how to calculate the value of sigma for ns and np. We are taking the example of potassium. So calculate sigma and Z effective for 4s electron in the K, that is potassium. So we are calculating the sigma value for 4s. So that falls in this category. So first of all, we have to write down the electronic configuration of the potassium, then group them according to group the shells according to the value of n that we did. So this is 4s, that is nth subshell, n-1 shell and all the inner shells. 1s, 2s, 2p are all taken as the inner shell. So sigma, first of all we have to calculate sigma, then we can calculate the value of the Z effective. So sigma is equal to 0.35 into 0. Why it is taken as 0? Because we are calculating the value of sigma for 4s and only one electron is present in 4s. If we are taking that electron, if we are calculating the value of sigma for that electron, the remaining electron in the nth shell is 0 because there is present only one electron, so that's 0. Next, 0.85 into 8, that is n minus 1. So this is n minus 1. 6 plus 2 is taken as 8. So 0.85 into 8 plus 1 into 10. Why 10? All the inner subshell or all the inner shell electron is taken as n 1. So 1 into 10. So 6 plus 2 that makes the 10. So in this way the value of sigma comes out to be 16.18. Then calculate the Z effective. 19. What is the value of 19? Z. Z minus sigma is the value of Z effective. So 19 minus 16.18 comes out to be 2.20. So the value of effective atomic number for any electron present in the 4s for potassium is taken as 2.2. The next step is we have to calculate the value of any electron present in the n-1 d orbital. And you people know that n-1 d orbital is considered for the transition metal. So in this case, we would consider the transition metals only. So here are some rules for the n-1 d calculation. No contribution from ns electron. You people know that in the case of transition metal, the d orbital is n-1. The principal quantum number for d orbital is 1 less than the principal quantum number for the last principal quantum number. So this is n-1d that you can look here. If it is 3d, the outer shell would be 4s. So for the 4s electron, 0 contribution because that is present outside the 3d. So no contribution is taken for that. The second point, 0.35 for each electron remaining in the n-1d. So look at here example. If there are 3d5 and we are calculating the sigma value for one electron present in the d, the remaining electron would be 4, not the 5, because we are considering 1. So remaining electrons are 4. 1 for all electrons in n-1 s, n-1 p and all other inner shells. So in this case for the manganese, this is taken as the ns 0 contribution. This is 3d n-1d, remaining electrons are 4 and 3s, 3p, 2s, 2p and 1s. So all these are taken as the n-1s, n-1p and all the inner. So calculate sigma and Z effective for electron in 3d for manganese. Manganese belongs to the transition metal 3d transition series of the transition metals. So we have written the electronic configuration, grouped it according to the n value, then 0.35 into 4. Why? We are considering the 3d5. One electron is taken for the value calculation of the value. The rest of the electrons are 4. Plus into 1 into 18. n-1s, n-1p and all inner shells. So 6 plus 8 makes 8. 8 plus 8. 16 plus 2. 18. So 1 into 18. So value comes out to be 19.4. So 19.4 is the value of the sigma for Mn, and the Z effective for Mn would be 25 atomic number. Z minus sigma is equal to 5.6. So this 5.6 is the value of effective atomic number for one electron present in the n-1d subshell of the manganese. So this was all about the Slaters rule. You have to practice some examples, and if you find any discrepancy or any ambiguity in doing this, you can post your question in the comment. So we would meet in the next video. Up till Allah Hafiz.